If I ask you to count how many apples there are, it's easy enough. There are only a few objects. We can count them, one by one, like so. But if there are many more objects, then it gets more difficult. But if we arrange the objects in a regular pattern, like this, now we can use multiplication to get the total number of objects without counting them one by one. So multiplication is the basic operation for counting. The word multiplication comes from Latin. It means many folds. So for example, let us start with this sheet of paper. We have one layer. But now if I fold a sheet of paper in half, I get two layers. And if I fold the layers once more, now I get twice as many layers for a total of 4. So each fold is a multiplication, and the final number of layers is a product of all the folds. Now, each fold can be a different size, that is a different number. For example, let's start with these 2 apples. Now let's fold by 3. That is, each apple creates 3 more, which means that I need to multiply by 3, and the total number of apples that I have is 2 times 3. Now, let's say each of these 6 apples in turn creates 4 more apples. So now I need to multiply by 4 to get a total of 2 times 3 times 4, which is 24. So the idea of folding appears in many places in computer science, except that we are not going to be counting actual physical objects like apples. For example, if we can count how many steps some piece of code takes, we can estimate its time complexity. So we'll next go over a few such computer science applications. One application is nested for loops, just the one shown here. We can ask how many times will the loop execute? Specifically, how many times will the word hello be printed? Okay. So in this case, the outer loop variable I goes from 0 to 4, which is 5 iterations. But each of iteration of this outer loop will start the inner loop. Variable j takes the values 0, 1, and 2. So that is, each inner loop has 3 iterations, a folding by 3. And so the total number of iterations is 5 times 3, which is 15. And that is the number of times the word hello will be printed. Now let's consider, let's consider this nested for loop, which is only slightly different from the previous one. Specifically, the variable I now goes from 10 through 14. How many times will hello be printed now? Well, the answer is again 5 times 3. Okay. And note that what matters is the size of each fold, that is the number of iterations, and not the actual value of the variable. So next is a slightly more complex example with 3 nested loops. Again, how many times will hello be printed? Okay. Well, in this case, we have 3 folds. The outer loop I iterates 5 times. And for each iteration of this outer loop, the second loop with variable j will iterate 3 times. So that's a fold or a multiplication by 3. And then for each of these iterations, the third loop with variable k will iterate 7 times. So this is a fold or multiplication by 7. So therefore, the total number of iterations in this case is a product of 5 times 3 times 7, which is 105. Now let's look at another application of counting. Okay. Suppose you wanted to know how many 2-letter words are possible where the second letter is a vowel. Okay. So note that in English, there are 26 letters in the alphabet, and of these, the 5 letters A, E, I, O, and U are considered vowels. So examples of such 2-letter words are AA, BA, BE, and so on. Okay. So in this case, the first fold is the first letter, which can be any of the 26 letters in the alphabet. And the second fold is the second letter, which can be any of the 5 vowels, A, E, I, O, U. Okay. So the total number of possible words is 26 times 5, which equals 130. So note that we can systematically print out all such possible words also with a nested loop, similar to what we saw previously. So here's a slightly more complex problem. Now, how many three-letter words are possible? Now, where the second letter is a vowel, and the first and the third letters can be any letters of the alphabet. So again, we have 26 letters in the English alphabet, and 5 of these are considered vowels. So examples of such words are AAA, AEB, BAD, and so on. Okay. So in this case, we'll consider each letter to be a fold, and so we have 3 folds. The first and third folds can be any of the 26 letters in the alphabet. The second fold can be one of the 5 vowels. So therefore, the total number of possible words is 26 times 5 times 26. Right? So you may want to try to write a C++ code to print all such 3-letter combinations. Now let's consider a special case where all the folds are the same size. The question is, how many 3-letter words are possible where each letter can be any letter from the alphabet? So examples of such words are AAA, AAB, AAC, and so on. So here again, we have 3 folds, but each of the 3 folds can be any of the 26 letters in the alphabet. So the total number of possible words is 26 times 26 times 26, okay, which is 17,576. And this number can also be written as an exponential, that is 26 raised to the power of 3. Now let's calculate how many 4-letter words are possible. Okay, some examples are shown here. Now we have 4 folds, each of size 26. So therefore, the number of possible 4-letter words is 26 times 26 times 26 times 26. That is 26 raised to the power of 4. So you can see the pattern here. In general, if I want to calculate how many words with n letters are there, I can multiply 26 with itself n times, and that gives me 26 raised to the power of n. So exponentials come in when the folds are all of the same size. Another place where we see folds of the same size is truth tables. So a truth table lists all possible combinations of values that you can assign to a set of true or false variables. So how many rows are there in the truth table with one variable? Well, the truth table looks like this. And since the single variable can be either true or false, there are 2 rows. Now let's look at a truth table with 2 variables. Okay, so how many such rows are there? So note that each variable of my single variable, each value, true or false, in turn gives rise to 2 new rows with values for the second variable. So that is a fold by 2. So the total number of rows in this case is 2 times 2, which is 4. Similarly, to get a truth table for 3 variables, note that each row of the 2 variable table gives rise to 2 rows, one for each value of the third variable. Okay? That is, we again fold by 2. So the total number of rows is 2 times 2 times 2, or 2 raised to 3, which equals 8. So in the general case, if there are n variables, there will be 2 raised to n rows. Now, moving on to another application. So another place where such counting helps is calculating the maximum number of undirected edges in a graph. So recall that an undirected edge connects 2 distinct vertices of the graph, and the order does not matter. So the question is, what is the maximum number of edges possible in a graph with, say, 7 vertices? Well, the first vertex of an edge can be picked in 7 ways. Okay. And for each of these, the remaining 6 vertices can be picked as a second vertex. So altogether, I have 7 times 6 pairs. But notice that I'm counting each edge twice. For example, I can count the edge AH twice, once picking A first and then H. But later, we also pick H and then A. So the total number of distinct edges is only half of what we calculated earlier. So we need to divide by 2 to get the maximum number of undirected edges, which would be 7 times 6 over 2, or 21. So calculating the maximum number of edges in a graph is a special case of counting without repetitions. We can think of each edge as picking 2 out of the 7 vertices without repetitions. Now, counting without repetitions occurs often enough that there's a special formula for this, and is written 7 choose 2. So in general, the maximum number of undirected graphs in a graph, the number of undirected edges in a graph with n vertices is the number of ways of picking 2 out of n, which is n choose 2, and is given by this formula n times n minus 1 divided by 2. Another application of counting without repetitions is in building data models. So often we have data for several variables, but a particular model will need to use only a few of the variables. For example, say we have 6 variables, say height, weight, age, income, family size, the number of hours of sleep. And I ask you, how many ways are there of picking 2 out of these 6 variables? Okay, so examples of these are, height and weight, height and age, height and income, and so on. Okay. So the number of ways of picking 2 out of the 6 variables is given by the formula 6 choose 2, which is 6 times 5 divided by 2, which is 15. Okay. And so we'd say that there are 15 such possible models. If I ask you how many ways are there of picking 3 variables out of these 6 without repetitions, again, we can use the same formula, which now becomes 6 choose 3. And the expansion for this formula is given like so, and gives us the answer, 20 such models.